If you like the video, please subscribe Technical PCT channel and click the bell icon to get the latest videos.
Good morning, students. Welcome to Sri Chaitanya online classes again. Well, happy to be with you once again. In last class, we started this chapter, electric potential and capacitance, right? Then just we recall what we discussed in last class. What is electric potential? Electric potential. It is represented with V and W by Q naught. Work done to bring a unit positive charge from infinity to a point in the field is known as potential at that point. This is already we discussed in the last class. Formula is W by Q naught. See, if you think this is the field, this is a point in the field. To bring a unit positive charge from infinity to this point, what if W is the work done, then potential at this point be W by Q naught. Let we are bringing a charge Q naught from infinity to this point. To bring charge Q naught, work done is W. For unit charge to bring from infinity to this point in the field, work done according to the definition it is equal to V. For charge Q naught, W is the work done. For unit charge, what is the work done? W by Q naught. This is considered as potential at this point. And we discussed potential difference. We discussed potential difference also. What is potential difference? If there are 2 points in the field, point A, point B, to bring a unit positive charge from one point to the another point against the field is known as potential difference between these 2 points. This is also we discussed in detail in the last class. See, if field is acting in this direction, like we are bringing a charge Q naught from A to B in this direction against the field. To bring the charge Q naught, work done is W. Q naught, work done to bring charge from A to B against the field is W. Then to bring unit charge, potential difference, we down to the PD, potential difference, we write it as VAB. It tells you it is coming from A to B. VAB represent charge is coming from A to B, which is equal to VB minus VA. Potential at the point B is VB. Potential at the point A is VA. Then potential difference between the points A and B is VB minus VA. Right? According to the definition, it is equal to work done to bring a unit positive charge from the point A to B against the field, right? For bringing the charge Q0, if W is the work done, for unit positive charge, how much? W by Q0. This is potential difference, right? If you observe the two formulas for the potential and for potential difference, see, this is also W by Q0. This is also W by Q0. But only difference is here we are bringing the charge from infinity to a point in the field. Here we are bringing the charge from one point to the another point in the field. Right? That is the only difference. As formula W by Q0. There also W by Q0. Well, see from these two formulas, if you are asked what is the unit of potential and potential difference, potential and potential difference, SI unit for both potential and potential difference. Formula is W by Q0. So this is simply for work, SI unit is joule, and for charge, coulomb. So joule per coulomb. But in general, we don't use this joule per coulomb. We call this as volt. Volt. So anyway, what is the unit of potential or potential difference? 1 volt. We write like this, 1 V, which is equal to 1 joule by 1 coulomb. 1 joule by 1 coulomb. Right, students? So what is the unit of potential difference? SI unit of potential or potential difference is joule per coulomb or volt. 1 volt is equal to 1 joule per 1 coulomb. Sometimes they ask you to define this volt. Definition of volt. Definition of volt. See from the formula, from this, 1 volt is equal to 1 joule per coulomb, 1 coulomb. So how to define it? How much is the work done? 1 joule. To bring how much of charge? 1 coulomb. From where to where? From infinity to a point in the field. If you are asked to define 1 coulomb, if 1 joule of work done, 1 joule of work done to bring 1 coulomb of charge. 1 coulomb of charge one joule of work done to bring 1 coulomb of charge from infinity to a point in the field, then potential at that point is 1 volt. If 1 joule of work done to bring 1 coulomb of charge from infinity to a point in the field, then potential at that point is 1 volt. Right? If you want to tell in terms of potential difference as 1 volt, how can you say that? If 1 joule of work done to bring 1 coulomb of charge from, instead here, from one point to another point, from one point to another point in the field, then potential difference between those 2 points is said to be 1 volt. Right? Even if you want to write the potential difference as 1 volt, in terms of potential difference, definition of volt, you can write like that. 1 joule of work done to bring 1 coulomb of charge said to be 1 volt. Right? Next. See, in last class, we derived an expression for potential due to a point charge. This is a point charge given to us. Let that point charge is Q or capital Q. Point charge. You are asked at a distance r from this point charge, at a distance r from this point charge, here, what is the potential? What is the potential due to this point charge? Right? Due to this point charge, at a distance r from that, what is the potential? Right? We derived the formula for this. What is that formula? V is equal to 1 by 4 pi epsilon naught Q by R. This is an expression for potential due to a point charge at a distance R from naught. 1 by 4 pi epsilon naught Q by R. Right? If I place a negative charge here, if I place minus Q, what is the potential at a distance R? Here, what is the potential? See, potential is 1 by 4 pi epsilon naught minus q by r. If charge is positive, due to this charge, potential is also positive. If the charge is negative, due to this charge, at this point, potential is also negative. Right? Positive charge gives positive potential, negative charge gives negative potential. Note points. Positive charge, potential is also positive. Due to negative charge, potential is also negative. Whenever you are calculating potential at any point, if charge is given positive, take positive charge plus q here. Given negative, take its sign also, minus q by r. That tells you positive charge creates positive potential, negative charge creates negative potential. Right? One more. So, a doubt, is the potential a scalar or a vector? Is the potential a scalar or a vector? See here there is no direction saying. Potential from the definition what it is, work done to bring a positive charge from infinity to a point. It is work done. We know work is a scalar, right? So potential is also a scalar. Note point is potential is a scalar. Potential is a scalar, right? Whenever you are dealing with problems related to potentials, remember that it is a scalar. In last chapter, we totally discussed on intensity of electric field, E, capital E. It is a vector. Potential is a scalar. Remember that. So whenever it is a scalar, no need of direction. Only when charge is given positive, take positive, charge is given negative, take negative. Simple. Right? So it is a scalar. Come on, note down. Well, potential due to multiple charges. Potential at a point due to multiple charges means number of charges. Potential due to multiple charges at a point. Let us see. Here is the point. This is a point. O. Here I placed one charge, Q1. Here another charge, Q2. Here another charge, Q3. like number of charges. Here another charge Q4, like so. Our question is, what is the net potential at this point due to these number of charges? Let this first charge distance R1. The second charge is at a distance R2 from this point. This charge is at a distance R4. This charge is at a distance R3, like so. What is the potential at this point due to this number of charges at that point, right? Let potential at this point due to Q1. Potential at O, at point O, due to Q1, V1 is equal to, what is the formula? 1 by 4 pi epsilon naught Q1 by R1. Yes, sir. Then what is the potential due to this R2? Potential at O due to Q2, V2, 1 by 4 pi epsilon naught Q2 by R2. In the same way, due to this Q potential at O due to Q3, V3, 1 by 4 pi epsilon naught Q3 by R3. Like due to n number of charges, potential at O due to Qn, n number of charges, Vn, 1 by 4 pi epsilon naught Qn by Rn, right? Alright. What is the net potential at this point? What is the net potential at this point? To write net potential, I'll do one thing. Here, potential at O due to Qn, n charge, n number of charges, Vn, 1 by 4 pi epsilon Qn by Rn. The net potential at O, V is equal to simply V1 plus V2 plus V3 and so on Vn. See, it is just algebraic sum of all the potentials due to individual charges. Potential at a point is equal to algebraic sum or scalar sum of potentials due to individual charges, right? So if you are asked to write the potential, V is equal to, see V1 is what? 1 by 4 pi epsilon naught Q1 by R1, Q2 1 by 4 pi epsilon naught Q2 by R2. So what is common in all those? 1 by 4 pi epsilon naught common. Take it out. 1 by 4 pi epsilon naught. Then write down Q1 by R1 plus Q2 by R2 plus Q3 by R3 and so on Qn by Rn. That's it. This is the net potential at this point. Right? PU point of view, important question. PU point, important question. Right? One thing remember, whenever you are taking net potential, if charge is negative, take negative with negative. Charge is positive, take positive there. Just take their algebraic sum or scalar sum, just like adding numbers. You add them, you get the net potential. There is no need of direction because potential is a scalar, right? Come on, note down. Well, if you want to write, you can write the statement. Net potential at a point, net potential at a point due to number of charges. Net potential at a point due to number of charges is equal to algebraic sum of potentials due to individual charges at that point. Due to algebraic sum of potentials due to individual charges at that point, right? Once again, I'm telling you, important question. PU. Next. Let's see some examples of this. See here is one charge. One charge. 2 coulomb. Here is another charge. 4 coulomb. 2 coulomb, 4 coulomb. They are separated by, let us say, some 4 centimeter, separated by a distance 4 centimeter. You are asked, what is the potential at the midpoint? What is the potential at the midpoint due to these two? Due to these two. What is the potential at this point? Oh, what is the net potential at this point? See, according to our theory, potential at this point is equal to sum of the potential due to this charge, sum of the potential due to this charge. V1 plus V2. What I said, where is this point? Midpoint. If this is 4 centimeter, 2 centimeter, 2 centimeter. Right? Come on, write down. V. What is common? 1 by 4 pi epsilon naught common. First charge, let's take it as Q1. Take this one as Q2. Q1 by R1 plus Q2 by R, right? 1 by 4 pi epsilon naught Q1 2 by R1 2 centimeter, 2 into 10 power minus 2, okay, plus Q2 4 by R2 2 centimeter, 2 into 10 power minus 2. From this first charge, this is R1 and this is R2. From the second charge distance is R2. From the first charge distance is R1. Right? 1 by 4 pi epsilon naught is what? 9 into 10 power 9. 1 by 4 pi epsilon naught. Right? Then, if this 10 power minus 2 also take out, what remains in? 2 by 2 plus 4 by 2. So this is 9 into 10 power 11. If minus 2 goes up, plus 11. 9 into 10 power 11. 1 plus 9 into 3 into 10 power 11. 27 into 10 power 11 volt. Right? This is the way. Come on, note down. What you understand from this? Due to this charge potential, just I took their potentials and I add them up simply. No directions assigned because potential is a scalar. Next. In the same problem, same dimension, same values, a small change I am doing. I am taking this one as minus 4C. Minus 4C. Second charge. First charge Q1 2 coulomb. Second charge Q2 is equal to minus 4 coulomb. Now I took 4 centimeter distance between them. What is the potential at the midpoint? Same question. So where is the change in the problem? 1 by 4 pi epsilon naught same. Q1 by R1 plus Q2 by R2. No change. 1 by 4 pi epsilon naught. What is Q1 here? 2 coulomb. 2. Distance 2 centimeter. 2 into 10 power minus 2 meter. Okay. Plus Q2 minus 4 coulomb. Minus 4 coulomb. Minus 4 by distance 2 centimeter. 2 into 10 power minus 2. Same. Here, what I get? Minus. Here, what I get? Minus. Here, minus 1. Here, minus 9 into 10 power 11. I got negative potential, right? Like that. So, what you understand here? Whenever charges are given negative, take them as negative. Take the charges along with their polarity and find the potentials. Take their algebraic sum. You will get the net potential at the point. Okay? Next. Come on, note down. I'll ask you a small question. This is a triangle, equilateral triangle. Here I placed a charge 2 coulomb. Here I placed a charge 3 coulomb, 2 coulomb and 3 coulomb. The side length, let us say 1 centimeter. Due to these two charges, what is the net potential at this point? Due to these two charges, let's take it as Q1 and take it as Q2. From this charge distance is R1. From this charge distance is R2. Okay. Then you are asked, what is the net potential at this point? What is the formula for net potential? Net potential V is equal to simply V1 plus V2. V1 plus V2. See, in those what is common? 1 by 4 by epsilon naught. Q1 by R1 plus Q2 by R. Right? Then, what is the final answer? See there, 1 by 4 by epsilon naught, 9 into 10 power 9. Q1 is what? 2 coulomb. By R1, 1 centimeter, 1 into 10 power minus meter. Plus, because this is also positive, 3 coulomb, Q2. By R2, it is also 1 centimeter. 10 power minus 2, right? So, 9 into 10 power 9 by, bring the 10 power minus 2 outside. 3 plus 2, 5. Then what you got? 9 into 10 power 11, it goes up, into 5. 45 into 10 power 11 volt. That's it. From this particular example, what we understand, charge may be here, or charge may be here, or charge may be at somewhere. That point may be at somewhere. To find the potential, what we need? What is the charge? What is the distance? Charge distances along with their polarity, whether positive or negative. If we know, we can calculate the net potential at that point. Okay, note down. Well, students, tomorrow we'll see some more examples. Just go through the previous topic.